Hello, Mr. Jones here. And right now we're going to be going through the AP Chem notes, pages 47. No, we're going to end on 47, 45 to 47. This will be the last set of notes for the solutions unit. So at the top here, I mentioned a review of what osmosis is. They used to teach osmosis in biology class. I'm not sure if they still do, and it seems like a significant number of you skip regular biology because you plan on taking AP biology. So I'm just going to go through what it is. So I have a drawing up here, and I'll make it a little bit bigger. Let's say you had a container, and you put a membrane in the middle called a semi-permeable membrane. That means that certain things can pass through and other things can't. And let's say that we just put pure water over here, and we put some sort of solution on the other side. So over here, I'll copy my picture up there. Let's put 2 molar sodium chloride. It's really strong for sodium chloride, but we'll just go with it. And let's say that this membrane, the semi-permeable membrane, only allows water to move. So only water can get through. So the salt particles can't. What happens here is that nature doesn't like this. Nature doesn't like these two situations touching each other. Of course, if they were in separate containers, that wouldn't be an issue, but they actually get to contact each other through the semi-permeable membrane. And so what nature tries to do is it tries to make the concentrations equal. And since the salt can't move, the only thing that can happen is water must go this direction. And that's what osmosis is. Now, what nature will try to do is, in an attempt to get these two solutions equal, well, I shouldn't call the one on the left the solution. So the water and the solution on the right equal, it will continue to try to put water on the right side. Of course, they'll never be equal because the left side doesn't have any salt. And so no matter how much water you put into the right side, you're always going to have some amount of salt. Now, what will happen over time is as the water moves to the right, the solution on the right will rise. Let me make my container a little bigger. And the solution on, again, I shouldn't say solution, the water on the left will lower until we get a situation like this, where there's less water than there originally was. And now there is some concentration of salt that's less than 2 molar. Now, it doesn't keep going forever until the water's gone, because eventually you have a situation where gravity's pushing down on this. And eventually gravity says, oh, no, you don't. That's enough water. And then you reach a state of equilibrium in which you still have water going to the right, but you also have water going to the left because of gravity pushing it, squeezing it over there. And of course, if we set this up in the lab, the amount of change of liquid level would not even be perceivable in this particular case, or it would be very small. I mention here that there's a demo that I like to do with dialysis tubing, and I'll set that up in class for you to see. What I do is I take this tubing that only allows water through, and I put concentrated sugar inside the tube. I put water outside the tube, and what's going to happen is the water will go into the tube, and the solution level in the tube will get higher and higher and higher. It's not quick, but it's noticeable within usually about 10 minutes. Of course, I had to mention that osmosis makes pickles. what happens is you put the pickle in a super concentrated solution, and water leaves the pickle, which is why it starts as a cucumber and becomes a wrinkly pickle. And this is also how desalinization plants work. What they do is they do what's called reverse osmosis that I'm going to talk about in a little bit. Now, this effect of the water trying to move creates a pressure called osmotic pressure right here. And the symbol we're going to use is the pi symbol. It has nothing to do with 3.14. It's just the symbol that was chosen. I don't know why that was chosen. And let's take a look at these pictures. So similar to my initial setup, we have pure water on the left, some sort of solution on the right. So you can imagine it's the same thing, it's a water solution. And we have a piston up here that we can either not push on or we can push on if we want. Imagine a hand pushing down on that. If the osmotic pressure, pi, is greater than what we're pushing down on, so let's just say there's a pressure of our hand pushing down on this. If the osmotic pressure is higher, then water will continue to move over from the pure to the solution, and that would be called osmosis. And the piston would, of course, get pushed up, showing an increase in the volume on the right side. However, it's possible for us to push really hard. Again, imagine pushing down on this. If we push harder with more pressure than osmosis is trying to happen, we can actually reverse it. We can actually send water from the solution back to the pure side. It's because the amount of force that is pushing from the pure side is weaker. We are winning. And this is what I mentioned with desalinization. This is what they do, is they set up a system. It's, of course, much more complicated than this drawing. And they put a lot of pressure on salt water from the ocean usually, and they push the pure water out of it. Now, there are environmental concerns because then you're left with a saltier solution that you have to dispose of or recycle back in the environment. And I don't really understand all of the details, but it's something that needs to be considered, especially as more places around the world are starting to build desalinization plants next to the ocean. In fact, my city just built one, Huntington Beach. They just recently finished it. I'm not sure if it's running yet, but probably is. And I know it was quite a complicated political situation. All right, moving on. Of course, we can calculate the numbers in this. I think I just messed up my notes, but whatever. I'll just deal with it when we get to the right spot. Yeah, it's separated, but that's okay. All right, what a surprise. If we go back to PV equals nRT, it's back. It's crazy how often this thing pops up. I often think if I just wrote this equation, the master equation with Gibbs free energy, and probably a couple others, I could probably just say, there you go. That's all the chemistry summarized in just a few equations. But anyway, we're going to replace pressure with pi, the osmotic pressure. If you take the moles on the right here and you divide by V in liters, so that, and if that's in liters, that's defined as molarity. So what I can do is I can replace that with an M and you get mert. Or if I write the whole thing out, you get pi equals mert, in which pi is osmotic pressure, M is molarity, I is the Van't Hoff factor, R is the same R that we've been using for a long time, and T is temperature in Kelvin. So for example, calculate osmotic pressure, 0.10 molarity, non-electrolyte means I value of 1, 25 degrees, just plug all the numbers in, and you get 2.4 atmospheres. So that's how much pressure osmosis is attempting to occur with. So again, if we were to set up a system with a piston like in the picture above, if we push with 2.4 atmospheres, we would reach almost like a tug of war, but in this case it would be a push of war, in which osmosis stops. Now, of course, what would really happen is equilibrium. Water would keep moving, but it would be moving in equal rates, both forward and reverse. But as far as an outside observer is concerned, equilibrium says that the situation stops. If we push with more than 2.4 atmospheres, then we get that reverse osmosis situation. All right. Next colligative property, boiling point and freezing point changing. All right, first boiling point. So in order to boil, what must happen is the vapor pressure of the liquid has to equal to the pressure above its surface, and we talked about that earlier, in order to compete with it. And in the case of pure water at sea level, under normal atmospheric conditions, this happens at 100 degrees Celsius. If you put stuff in the water, what it does is it makes it harder for the water to evaporate. So it makes this process here more difficult. In other words, there are interactions between the solute and the water solvent that cause the water to not be able to vaporize so easy. So you have to heat the water up more so that you can get to this point where its vapor pressure is able to compete with the atmosphere. And that's why the vapor pressure the vapor pressure of the liquid goes down, so you have to heat it up more, and that's why the boiling point of the solvent goes up. And so we have an equation here, delta T, the B just means boiling point, equals KMI. B, again, refers to boiling point. K is a constant, M is molality, and I is the Van 't Hoff factor. Now, this is a case where molality is more useful than molarity. So I think when you first hear about molality, you think, this is lame. Why are we bothering with this? Well, there are times where it's actually useful. And you can see that there's these constants on page 267. So you'll need that for some of the homework. And I mentioned this, by the time we get to this lesson, we have already done the concentration lab. But had you known about this concept, you could have used this concept to solve for at least the molality and probably other forms of concentration. What you could have done is you could have measured the boiling point of the solution you were given and then compared that and used this equation to what it's supposed to be for pure water, and you can actually solve for the molality. And we'd have to go through the math and see what other forms of concentration we could solve for. We might have to get some other data, but this would have been one technique to do it. And I have had kids do it in the past. They've looked this up before we even taught it. All right, next section. All right, freezing point goes down. It again has to do with the interaction of the solute particles and the solvent. Now it says they get in the way. I don't really know if I like that phrasing very much. I mean, to some extent, the solute does get in the way of the solvent finding each other, because of course, if the solvent is trying to freeze, that's when it is interlocking with its other pieces. It does get in the way, but there are also certain interactions. It could be an ion dipole or other intermolecular forces. So there's a variety of things happening. So it's not just a physical getting in the way, it's also different interactions. And that makes it harder for it to make a solid, and so you have to get it colder. So the equation is the same, except notice the little F for freezing point. So if we take a look at this first example, estimate the boiling point of a 0.2 molal solution of sodium chloride. So here's our equation, delta T equals KMI. They told us the constant, it was given here. They told us molality, I values too, because it's sodium chloride, and you get a delta T of 0.208. Now you need to think, does this mean that it's going up by 0.208 or is it going down by 0.208? In the case of boiling point goes up, freezing point goes down, so that means that it would be 0.208 higher than normal. Well, in the case of water, it's normally 100, add 0.208, and so you can see it goes up a little bit, like that. We'll assume that the 100 is perfect. All right, antifreeze. In a car with a typical internal combustion engine, you've got a radiator and it has antifreeze in it. And one problem with this is if you were to fill the radiator with just water and the weather got cold enough, the water would freeze. And as we discussed earlier, the water would expand when it freezes, and that would break things. It'd probably break your radiator and it'd break things in your engine. So you need to put antifreeze into the coolant system to keep it from freezing, hence the name. It also has other properties that cut down on corrosion of the metal parts. So that's why even where we live, we still put the antifreeze in there, but it's not such a freezing concern. It's more of a let's keep the corrosion to a minimum. But anyway, let's take a look at the situation where it might freeze. So the problem says we're doing 50 cc's, same thing as milliliters, of ethylene glycol, and we're doing 50 grams of water, which basically, this is a 50-50 mixture, and so it's hard to determine who is the solute and who's the solvent. But since water is typically the solvent, we'll just say that the ethylene glycol is the solute. And I want to know the new freezing point. In other words, does this stuff actually freeze significantly lower than the normal zero of water? So I took my milliliters of ethylene glycol and it gave the density, turned it to grams to moles. So here's my moles of ethylene glycol. I plugged that into the molality equation. So 0.902 moles of ethylene glycol. I turned the grams of water into kilograms because remember, molality is moles solute divided by kilograms of solvent, and it must be kilograms. And we get 18. We then plug that into the delta T equals KMI calculation. Here's KF for water. Molality we just solved for. In this particular case, how did we know that it was an I value of 1? It wasn't made very clear, but if you take a look at this, this looks like a typical molecular thing, an organic thing. So in that case, you can assume it's a 1. Basically, unless you have a reason to think the I value is greater than 1, just go with 1. And we get that the change in temperature is 33.6, but this time it's 33.6 degrees lower than normal. So 0 minus 33.6 is negative 33.6, which, yeah, that's significantly lower. And again, it's called antifreeze because of that. Moving along. There's another problem. What do we have this time? Student. Oh, a student. This time they were specific. They actually tell us something. A student dissolves 1.5 grams of some compound in 75 grams of cyclohexane. All right, cyclohexane is an organic nonpolar solvent. It would pretty much be 6 carbons like that. And there'd be some hydrogen sticking off of it that we usually don't bother drawing, like so. That'd be cyclohexane. And it's a good example of a nonpolar situation. In this case, because it's nonpolar and molecular, we can just assume that it has an I value of 1. So things that dissolve in it are going to have an I value of 1. So again, the problem's not super clear, but this does make sense. We know more about the person doing this now, measures the freezing point to be 2.70 degrees Celsius. Now, at first, that seems weird. People go, wait, what a second. Students often at this point, they say, I thought that the freezing point always goes down. How is it that it's 2.70, which is higher than 0? It's because you're obsessed with water. We're not talking about water right now. We're talking about cyclohexane. So you don't even know what its normal freezing point is yet. So the 2.70 degrees Celsius is actually lower than what it does normally freeze at. So it is okay because we're not talking about water. And sure enough, in the very next sentence, it says pure cyclohexane is 6.50. So, okay. So it actually did go down from 6.5 to 2.7. I've got the Kf value here. I want the molecular mass. Okay. Of the compound, which is the unknown. We don't know what it is on purpose, because if I told you what the compound is, you would just look it up on the periodic table. And we already know that it was 1.50 grams of this unknown compound. So at the end, we're just going to take the 1.50 grams and divide by moles, but we have to solve for moles first. So temperature change was 3.08 degrees Celsius. This right here is delta T equals K mi. I plugged in the temperature change here, plugged in the constant molalities, what we're solving for. I value is 1, we get a molality of 0.9190. And that means so many moles of solute per so many kilograms of solvent. And it said how many kilograms of solvent there were. It said 75 grams. So I converted that to kilograms. And now we can solve for moles of solute. And now that we know that, we can do grams divided by moles to get the molecular mass. And again, to remind you, molecular mass and molar mass are the same calculation. It's just that in molecular mass, we're looking at a single molecule. So you don't want to say grams per mole. You can say AMU is the best thing to do. All right, we already talked about earlier how the I value is often not what we assume it to be. It's often less than that. And so this, kind of like when we talked about with vapor pressure, we don't get exact ideal situations. And so there's going to be some deviations from what we calculate. And it's mainly because things don't split up like we pretend they do. And an important point is 3b. As the charge of ions goes up, what happens is they tend to not split even more. And so you get what are called ion pairs, where ions are still, they're dissolved, but they're still stuck together a little bit instead of the individual ions that we typically assume. And here's an example. If we were to compare sodium chloride in water and magnesium sulfate, we say that they both have an I value of 2. But it turns out that sodium chloride would be closer, let's just say 1.9, whereas magnesium sulfate might be, say, a 1.7 because the higher charge of the magnesium and the sulfate ions. Now, I mentioned this becomes more serious as you get higher concentrations. It's just because there's not enough water to surround every individual ion. So you start getting more of these ion pairs and maybe even chunks of ions that are more than pairs. And that does it all the way up through page 47.